One. Yeah. Well, my talk would be kind of devoted to practical merge of property-based testing and dependent types. We are on type-driven development workshop. I really hope that everyone kind of at least heard of dependent types. Is it right? Kind of, yeah. Okay. You'll see kind of several dependent types written on slides, and kind of probably it will be important. And I kind of I really hope that you will agree that property-based testing in general is really a cool thing. There is a lot of work showing that it is. But talking about type-drivenness and property-based testing, what does it mean to be type-driven? I claim that it is a way kind of to investing some effort in expressing the intent using types, probably using expressive type systems, and then gaining something of it. It can be kind of less code, or probably some better code, some more confidence in it. But what I claim is that we can have good tests out of it too. As a simple example, probably it's not really the most representative one, but it's a really simple one. Imagine the function that merges two sorted lists in a sorted list. Kind of, we want to tell, we want to test it that being kind of given to sorted lists, it indeed produces a sorted one. Well, how can we property-based test it? We need some generators of sorted lists. Surely we can write this generator by hand for kind of for an ordinary list type. Oh, I forgot to say that I'll be using Idris language as an example of code on my slides. So kind of that's why we have list type written in letters. So kind of it's not really difficult to write our own generators for sorted lists, for instance. But after that, we need to check that it indeed correct, that it has good distribution, and so on. It has to have good properties. Surely we can use not only generators for arbitrary lists. We can have a new type for sorted lists, but still we need to write these generators and check their properties. What I claim is kind of a worthy solution is to to write intent of sortedness in the type and then derive the rest with all good properties. What can it look like? Well, this is probably not the best example of sorted list expressed with dependent types, but still it works. We can express the difference with the normal list is in the cons constructor, and here we express that we indeed can prepend the x value to preserve sortedness. If we had some machinery to derive the complete and nicely distributed generator, then we just simply can write our property of for testing merge function using this generator, having some conversions. I mean, surely it won't kind of work for free. I mean, we can still make a mistake in our specification, but comparing to the handwritten generator of sorted list, it kind of it's still a declarative specification. I mean, type is a kind of something probably it's a little bit easier to think about, to reason about. library that derives this generator can provide you completeness and good distribution in some meaning of good, but this approach has its own drawback because you don't have full control of everything at your hands, but it's a cost of the approach. So let's try it. I'm describing real project that took place some time ago, and the aim was testing the new implementation of a new language. It was a a dialect of TypeScript, and it has both interpreter and compiler, and it has just-in-time optimizer in the interpreter. What property we wanted to test is something like this, that every semantically correct program in this language actually compiles, type checks. And also that every halting program, every halting semantically correct program actually can be interpreted and being compiled can be run successfully without any unexpected stuff. And that all these modes produce the same result. I think it's a reasonable things for this language. Specification can look like this. For instance, there is a list of statements type with some context. You can see that there is a function context, variables context, and since it's a point in the middle, there are variables before and after. We declare some new variable, and we extend the context. And for instance, there is an assignment. This is a primitive imperative language. So there is an assignment, and you can see that this one says that variable that is used must be in the context of variables, and the type of expression must correspond to this variable. So we expressed it in the type, and it's impossible to construct a value of this type that uses wrong variables or uses them with wrong types, and etc. I mean, there are a couple of more statements. The same is for expressions. Expressions also has these typing rules. So I won't stay on this more. We actually specify this language in a similar way using the TypeCheck library, which was being written during this project, and we specified only a pretty small subset of the original language. It was only for halting programs. I mean, we had loops, but with on a limited loops. We have some other type of statements, and we actually use some specification hacks to make the whole thing to work better. For instance, we didn't use names for variables; we used Debian indices for them, and some other stuff. In specification was not so long. I mean, it was a little bit more than 300 lines of code, and other stuff like and some other stuff like printing to the surface language and etc. And we, for some reasons, for some technical reasons, partially derived and partially handwritten generators, but the most significant part was actually derived. So what we found? We started generating these programs and checking our property, and suddenly we had a crash of a runtime that Yeah. We shrunk the example, and we had the following code. It is a minimal example. I mean, every single line is important, and every single type is important. You can see that, for instance, if you there is a class with one field, you can probably think that you can replace this type of this field with the whole class, and but then the bug won't reveal. So we kind of continued testing, and we found some type error. After shrinking, we found this type of bug. When we realized that after each time when you trying to index a very literal, you have the wrong result always. And just to show you another crash, this was the minimal example of this crash. I mean, every single line of code matters to kind of produce this result. And I ask you to imagine kind of human tester that can produce this type of test. Okay. Finally, we found pretty a lot of bugs in different parts of the system. It was not only optimizers in crashes, but also some bug in the code generator and typechecker. And we even found some bugs just during producing the specification. And I think that we repeated what is well known for property-based testing in general, but in another setting, that same property can find many bugs in kind of very, very diverse bugs, and very subtle bugs lie in the intersection of different features of the system. And property-based testing can find them. And property-based testing is cool, but what I claim is that the dependent types for property-based testing is also cool. Okay. Well, I have little time to dig into some details of what what can be difficult if you are kind of using or implementing property-based testing with dependent types. So kind of actually, it's not a trivial question to ask what is a generator itself. For instance, there is an indexed type of natural numbers less than the given number. I mean, having dependent types, you can easily think of this. Like fin2 is a type of 0 and 1, and etc. What is the signature of generators for this type? Actually, kind of, I say that we can think at least about two ones. One when the index is given, and another when index is generated with the value of this type. And it's kind of, sometimes we need one, and sometimes we need another. With more complex types, like with several indices, we can have a bunch of different generators. And connected with this question is, can generators be empty? Well, quick check, classic quick check says kind of yes, because you can at least filter arbitrary generator. Some libraries said no, we don't need that. It's really inefficient and so on. But we can't afford saying strictly no, because, for instance, we then can't afford this type of generators. So, but we found that if we just simply allow this, most of the time of generator actually spends in this kind of a backtracking or retrying this empty stuff. So, what the solution? We have our generators indexed by some emptiness. Well, in our library there are 3 variants, but I won't stop on the middle one because kind of it's a little bit too deep in details. Why? But using this index, we can say that, for instance, the first generator is indeed maybe empty, because sometimes we can ask for uninhabited type for generating values of uninhabited types. But other two generators are actually non-empty because we always can produce some value for any argument, or we can always produce such a bound that has inhabited. So how this kind of effectiveness is actually achieved in the following way. Internally, we don't have possibly empty generators in the clauses when our generation tree kind of splits, so that we won't spend any runtime in choosing, in traversing and backtracking this. But on the but on the surface, we actually allow this. Well, unfortunately, I won't explain in details what these types are. But what I want to say that actually what we have is that if we have some if we have some choice between different generators, and some of them are actually empty, that we kind of eliminate them at the construction of the generated expression themselves. We do it really early, and it saves a lot of time. There are also a lot of challenges in derivation of such type. Surely we don't support every single dependent type, and I'm not sure it's really possible. But still, we want some complete, total, and nicely distributed derived generators. For instance, if we want kind of a generator for lists of some bounded type, we want length of lists to be distributed evenly, in a sense, and each element to be distributed evenly independently. Okay. Well, there are a lot of other other things that we want from derivatives. Well, I'm not kind of, but I'm not stay on this for now. So basically, I have enough time. I mean, it's time to end. So thank you for your attention. And if you're interested, you can check both these slides and the code examples that I showed you yourself. Thank you.
So any questions?
Hi there. Great talk. Do you find, did you run into difficulties deriving generators for types where the proof is sort of held within the type? I'm familiar with like the generating good generators literature from the quick check space, but that usually deals with an inductive that is later applied to a data type.
Yeah, I even had some kind of examples of these challenges. I mean, for instance, when there are complex dependencies inside the type, the choose of order is really important. And sometimes, if we are talking not only about simple types that are kind of predicates over ADTs, but kind of dependent types that depend on something that depends also. There is a challenge in choosing which subgenerators you really want, and depending on signatures, there are different choices of efficient ordering, and it's a kind of I can't say that we solved this fully. I mean, we we understand sometimes the most efficient one. Sometimes we kind of reject producing such a generator, and sometimes we just producing non-efficient generators, unfortunately. And by the way, there is always, there is always a possibility in writing dependent type which is not possible to be generated efficiently. And we try our best, but kind of, yeah.
Okay, thank you.
Okay, I think we should thank the speaker and move on to.